Welcome back, Astronomy 1020, to your second part lecture on relativity, which of course is my absolute favorite topic in astronomy and physics. So if I get a little excited today, you know why. We also have a homework today on relativity, which will be weird and wacky. It's going to involve all of your favorite relativity effects like time dilation. I can see Christopher already losing it, okay? Let's start off by remembering our two postulates of special relativity. In 1905, Albert Einstein proposed two controversial postulates that would re-explain some key experiments involving light in physics. This became known as special relativity. Let me see here. In special relativity, sorry guys, one of these markers is the good marker, was proposed in 1905 by Albert Einstein. Do you guys remember what the two postulates of special relativity were? The whole basis for relativity? Someone regurgitate. Let me grab a marker, and when I come back, you will, oh, here's the marker. You're done. Regurgitate from your notes. Okay, Devin's got one. The laws of physics stay the same. It kind of rhymes. The laws of physics stay the same in all inertial reference frames. That tells us that, and the speed of light is a constant for all observers. Thank you, Devin. A nice contribution from Troll Society here. Okay, so, and the second one is the speed of light is a constant. People sometimes refer to the speed of light as a constant. There's a catchphrase associated with it. It's known as the invariance of the speed of light. I don't know if I am capable of spelling invariance. There's a vowel there. I don't know which one it is. Invariant, I think it's an A. The invariance, the speed of light. Now, let me say a few things to just get your noodle cooking here. At first, this is the key to things becoming weird in relativity. If you say the speed of light is a constant, you are basically breaking the Galilean transformation of velocities. The Galilean transformation of velocities is the common sense logic that says, if I'm traveling on a skateboard at 5 meters per second and I throw a ball forward at 2 meters per second, then that ball, with respect to the ground, will move at 7 meters per second. That is going to eventually break down because all observers have to measure the same speed of light. In a way, what you are doing is, if the speed of light is 300,000 kilometers per second, you are in an awkward way creating your own hard conversion factor that says 300,000 kilometers is equal to 1 second. In fact, when I took my graduate level general relativity course, where we used the legendary Green Schutz book, in this book, they don't measure time in seconds or hours or years. The unit of time is the meter. Things are pretty weird in this thing. Okay, now, today I want to actually eventually move on from relativity, although it's going to take a long time. What makes special relativity special is that it only deals with physics in a certain domain, a certain box, And that box is this one. Special relativity only works for inertial reference frames, so only for a velocity which is constant, okay? So if I was Darth Vader here, I'd say no accelerations, okay? That's how this works. No accelerations. It's a limited description of nature that deals with two different observers moving at constant velocities with respect to each other. Albert Einstein obviously knew that this was a limiting case and that in nature, there's really no such thing as no acceleration. Even if you travel at 90 miles an hour in your car on the way to work, you had to accelerate to speed up to that, and presumably you will have to decelerate to slow down and stop, okay? Einstein set out during the next 10 years to come up with a more comprehensive description of nature, which would deal with this wacky physics at velocities which were not constant. He wanted to eventually deal with accelerations. Now, what's cool about Albert Einstein is he's one of the few scientists who had a program or a plan he set out to do, and he actually accomplished his mission, although it took him 10 years. He eventually came up with the theory of general relativity. And this was published in 1915. 10 years it took him to work out the mathematics for this theory. And this is the theory that we actually want to deal with. This theory deals with traveling at the speed of light. And at first it set out to deal with accelerations, but it ended up becoming, in a kooky way, in a backdoor, unsuspected way, it ended up becoming a theory about gravity. So although special relativity, you might think of special relativity being a theory of motion, general relativity ends up becoming a theory of gravity. And we would like to talk about both of these today. We still have a lot of work to do in special relativity, but I wanted to give you guys a little bit of top-down structure so that you can see that there are two branches of relativity. First, the more restrictive special relativity, then the more expansive general relativity. Usually, general relativity is something you're not even allowed to study until you have mastered a complex mathematical technique known as tensor calculus, okay? Tensor calculus is like calculus in infinite dimensions. It's pretty wild. Not everybody gets to do tensor calculus, but we can understand some of the concepts behind both of these things, even at an astronomy 101 level, and it's really fun, as Christopher Leonard now knows, right? Nothing's more fun than relativity, right, Christopher? Okay. All right. I need to erase here. You've got your top-down structure. You know about special relativity and general relativity. Let's get back to special relativity. May I erase? Does anyone need a second? Elijah, you cool? All right. Okay. Once you propose the two postulates of special relativity, if you agree that they are true, a number of consequences, surprising consequences, develop from those postulates. Let's write down what some of the consequences of special relativity are. You will remember that in last week's class, I spent a significant amount of time attempting to derive time dilation. That's one of the first and most interesting consequences of special relativity. And the idea behind time dilation is that moving clocks run slow. You guys got to practice it a little bit during your twin paradox lab, but today I'll probably have us do a few more sample calculations. It's also going to occur. In our homeworks. Sorry. Today I'll introduce you to some of the other consequences of special relativity. I will not spend as much time deriving them because I don't have time to do that. The next one is called length contraction. Length contraction is the observation that moving objects will actually shrink or contract in length only in the direction in which they are traveling forward. Sometimes people describe it with a simple mantra: moving rods. And they choose a rod because a rod is essentially a one-dimensional construction. Sometimes we also choose rulers. Of course, a ruler technically has a thickness and it technically has a width, but who cares about that? The main dimension of a ruler, let's flip this around here. The main dimension of a ruler is forward. A moving ruler traveling close to the speed of light will actually contract in length along the direction of the measurement on the ruler. So we say moving rods or moving rulers shrink. And yes, we have proof of, well, proof is hard to come by, but we have support, observational support for this. An even weirder one has to do with, where is it? Where's my prop? An even weirder one has to do with mass itself. Traveling close to the speed of light affects the very mass of an object. It's called mass increase. Moving masses, I don't want to say grow, that sounds like a plant. So I'll just say moving masses increase. Not as catchy a phrase, but I don't know what else to do there. There are other consequences as well that are wild and interesting. Have you guys ever heard of this equation before? E equals mc squared. That comes as one of the consequences of relativity. The book even has a proof of its derivation. Arunsak, hit me.
Why do we accept this as like a usable principle if there's so many like consequences? You know what I mean?
Well, here's why, Arunsak. At first, people didn't, because scientists are a skeptical lot, right? And when he first proposed this and people began working this out, most people said, dude, what have you been smoking? This sounds crazy, just like you guys are saying. And then one by one, through laboratory experimentation, they quickly discovered that these postulates and these consequences explain the results that they see in a lab. Now, I believe I told you about one of them called the Hefele-Keating experiment. Were you there till the end of the class, Arunsak, where I told you about the two atomic cesium clocks they put on the jet?
I wasn't even in the last class.
Oh, well, we missed you.
Yeah.
Okay, so Arunsak, I wish you were, because you would have asked me some challenging questions, okay? Let me say this, Arunsak, for every single one of these postulates, I wouldn't be talking to them about them now if there hadn't been observational support that they exist. One of the ideas behind relativity is our foremost theory of motion and gravitation. Okay, so now we got to talk about what a theory means. Ever heard someone say, oh, evolution, it's just a theory. God put the bones there to confuse the dinosaur bones there to confuse the scientist, or whatever you want to say, right? You don't understand what a theory means to a scientist. A theory is the highest possible scientific principle you can have. You know, when you were in elementary school, someone probably told you that first there's hypothesis, right? And then as you go from hypothesis and you gain more support, you become a theory. And then your high school teachers who lied to you, they told you that when you finally prove something true, it becomes a law. In fact, nothing could be further from the truth. We only elevate something to the status of law in science once it has been proven false, once we are sure that it is not true, but we still keep it around because it's useful, you know, in the same way that something out of date might still be useful, like an old can opener or something. It opens a few of these cans, so we'll keep it around. The highest scientific principle or the highest scientific concept you can have is a theory, because in science, you never prove anything true. You just keep observing and observing, and you get more support for it, and you feel more comfortable. But scientific theories are like a dog that could go rabid and turn on you at any time. You always kind of keep one eye open. You don't sleep too soundly. But scientists are skeptical like that. They don't believe anything is ever proven true. They certainly believe things are proven false, okay? Anyways, I wouldn't be telling you about these postulates of Arunsak if they hadn't been tested not thousands, not tens of thousands, but hundreds of thousands of times in laboratories. Trust me, more will be revealed. Let me tell you about some other wacky consequences of special relativity. In the past, people used to think that the 3 dimensions of space were one thing, and that time, the inexorable flow of time, was another thing. Einstein discovered those 2 things are intimately connected. Now we occupy a 4-dimensional space-time. Okay, I'm going to bust out a kind of fancy sounding vocab term on you. Manifold, okay? A 4-dimensional space-time manifold. A manifold is like a coordinate system. Here. This in a way could be considered a manifold, okay? This is a coordinate space on which you move chess pieces. Other consequences of special relativity, which you will learn about in your homework today. Here's a weird one. I can't explain this to you yet. It's got kind of a funny name. It's called the failure of simultaneity. And this basically translates into the failure of simultaneous things. Put that on pause. We'll get to it. There's a couple of, there's a new version of the Galilean transformation of velocity additions. It's called relativistic velocity addition. This one will probably bore you guys the most, so I may not get to it. And I think there's something else that I'm missing. What else am I missing here? These are the big ones anyways. There's one other thing, but it's just not coming to me. Okay. Anyways, do you guys see that I have my work cut out for you? Do you remember how I spent a lot of time on time dilation? I will not be able to do the same level of detail. Obviously, once I started doing the algebra for time dilation, I saw you guys get wicked bored. So probably less is more in this context, okay? All right, now we got to do a little math and we got to understand some formulas here. So make sure you got those down. I'm going to sip my coffee. And then we're going to get to doing some maths. May I erase? We cool? Okay. Okay. Could we start by reviewing time dilation? I find that with these concepts, it's good to kind of repeat them a few times. Let's remember the setup that we had for time dilation. This will be helpful for Arunsak who missed our class. We have a train station in which we have an observer called Observer A. Observer A stands at the ground with a stopwatch measuring the time for an experiment involving a laser beam. Observer B is traveling in a train car at a very rapid velocity. So here's Observer B. And you will remember that the experiment was that Observer B fired a beam of light, a laser beam, from the bottom of the car to the top of the car. And both B and A are timing the experiment. for how long it takes the laser beam to travel from the bottom to the top of the car. Because A sees a different path traveled by the laser beam, and because both observers have to measure the same velocity of light, A will measure a different passage of time for the experiment than B will measure. The laser beam itself, the firing of the laser beam, is called the event. In relativity, the event is the thing that both observers agree they are trying to measure. Both observers agree this is to be measured. That's probably the only thing they're going to agree about, is they're both measuring an event. I want to tell you guys right now that the event, forgive me if I'm talking too fancy here, the event is frame dependent. Does anyone know what I mean by that? If I say that the event is frame dependent? Are you talking to me, Kaitlyn, or no? You're talking to, okay. Does anyone know what I mean by this? I'm just confirming that you guys, yes, Arunsak.
Do you mean like it's specific to someone's frame of reference?
Yes. And for instance, the laser beam, Arunsak, whose frame is the laser beam being fired in?
It's B.
It's clearly in B's frame, right? Now, Arunsak, unfortunately, you missed like what's cool about this. I had a whole derivation where I did this slow, and I don't have time to redo it for you again, but for your benefit, since you're talking to me, and since you're the only one talking to me, the difference between the two observers could be summarized by this slide here, 19. B will only see the laser beam traveling to the top of the car. But A is actually conscious that the car is moving forward. They usually put you in a train car so that you can't see outside the car. So the person inside the train car could imagine that they weren't moving at all, because constant velocity is the same thing as being at rest. So B thinks he's at rest, and he just sees the laser beam go from the bottom to the top of the car, and that's a short path. But A is watching the car travel forward, so he actually sees the laser beam start at the bottom and travel this much longer path. You can clearly see that this path is shorter and this path is longer. If both observers agree that the speed of light is the same, then A has to measure this time as being longer than B measures for that time, because the beams are traveling at the same rate, but this one has farther to go, right? And this creates this legendary formula called time dilation. And time dilation means moving clocks run slow. And you can watch the video from last class, but I eventually developed this formula. Sometimes to color code it to make things cute, I make A green and I make B blue. And so last class, I said that TA, the time it takes an event from observer's A perspective, is equal to TB's time, but it's modified by this special relativity whack factor, the square root of 1 minus your percentage of the speed of light squared. And this is the equation known as time dilation. Now, today it's time for us to change our perspective on things. When we first learned about time dilation in this setup, we at first considered A to be the observer who was at rest, and we secondarily thought that B was in motion. And I had a chat with Kaitlyn about this last time, where I said, who's moving? And Kaitlyn said, well, clearly B is moving because they're in the boxcar. But then remember, I kind of twisted that on its head at the end, and I said, couldn't B actually argue that he's at rest with respect to himself in the train car, and that it's actually observer A and the entire planet that's racing past him? Now, that might sound a little preposterous, But remember that inside of that inside of that blacked out train car, B has the same physical experience as an observer who is stationary. There are no forces or accelerations acting on him, so he could imagine successfully that he's at rest inside the train station. Because of this, it's kind of difficult to say who's moving and who's at rest. Perhaps there's a better way to look at this thing. Instead of talking about who's at rest with respect to the ground, it's better to say who is at rest with respect to the event, which is the laser beam. So professional scientists, when they write down the time dilation formula, instead of calling this TA and TB, they actually usually refer to A as the observer frame. So this is the observer. For instance, the observer in a lab or the observer at Earth. And they actually refer to B, even though it's in the train car, as the rest time. This is what is known as T-rest. B is considered the rest time because B is at rest with respect to the event. Okay, let's just prove that you guys can still handle this. Suppose B measures a length of time for the event to be 10 seconds. And suppose the velocity of the train car is 95% the speed of light. Let's have you guys do a calculation. If the velocity is 95% the speed of light, and the rest time in the event is 10 seconds, what will be the time measured by the observer? Can you guys compute that for me without any help? Before you go on to the next step, you need to prove to me that you can handle this little basic thing. I suspect some of you will struggle. In other words, take out your calculator and do it. Okay, all right, sorry. I didn't see that.
Is C the speed of light?
Yes.
Okay.
Arunsak, let me give you a little tip. You don't actually need to plug in the speed of light. Do you see why? If the velocity is 95% the speed of light, if I divide both sides by C, V over C is 0.95. So all you need to plug in the parentheses there is 0.95. Okay, that's it. So you don't actually need to plug in C. That's the first secret. How many seconds for observer A?
32.
Nicely done. How many of you got that? Or I should say, how many of you did not get that? Kaitlyn, what did you get?
I wasn't finished yet. I'm sorry.
All right, keep going. Chris, what did you get? There's only 4 people who are actually willing to become humans that I can talk to, so I have to pick on you guys. You guys get the best training. How many trolls have we got today anyways? Sometimes I forget there are trolls out there.
I got 32.
You got the 30, there's a whole bunch of trolls.
Yeah.
You got the 32 Arunsak? I'm proud of you.
Yes, sir.
All right, Cam, we hear you. Paul G got the 32. All right, it's good to know that you guys are there and you care. Just, Okay, Kaitlyn got it too. Killer. All right, hell. Then you guys are ready to take your next step into relativity. I need to now make things a little bit simpler for you guys, okay? By the way, which clock is the slow clock? The rest time or the observer time? Which clock runs slow?
Rest.
That's correct. 10 seconds means the rate of time is slower in the rest frame. Okay. In every relativity equation that I'm about to show you, and I'm about to show you a whole bunch, every relativity equation involves this factor, the square root of 1 minus v over c squared. Because of that, we can greatly simplify relativity problems if we introduce a new variable that deals with the velocity of the cart. And it is known in relativity as the boost. I will now introduce a simplification. Let me introduce the boost. The boost, which will have be defined as gamma, is your special relativity whack factor. It is the factor by which times get whacked. It is the factor by which lengths get contracted. And it is defined in the following way. We define the boost to be 1 divided by 1 minus v over c squared. Why don't you guys help me? Let's calculate the boost for a velocity of 90% the speed of light. If the velocity is 90% c, what is gamma? Could you guys figure that out for me?
.3.
Nice. The boost has no units. It is the factor by which times are dilated and lengths are contracted. The boost has a domain, a domain of always greater than or equal to 1 and always less than infinity. As you get closer and closer to the speed of light, the boost goes nuts. All right. Let's try a couple of other examples. I need to erase when you guys are done copying. All right. Let's come up with a completely hypothetical situation, but it's one that we should work out, okay? Let's say the professor leaves his downtown loft and drives in his van at 90 miles per hour to work in a straight line to CCRI, where a bunch of bored students are waiting at their desks, okay? Let's say a typical trip to travel from home to work takes about 20 minutes. 20 minutes for the professor inside the van. How long do the students have to wait if the professors are traveling at 90 miles per hour? First thing we're going to do is we're going to figure out our percentage of the speed of light, and we're going to do that kind of quickly, okay? So let's just go to Google and cheat a little bit. 90 miles per hour to, let's just say meters per second. 90 miles per hour is 40 meters per second, okay? First, let's ask ourselves, what percentage of the speed of light is this? What is our V over C? It's 40 meters per second divided by, in meters per second, the speed of light is 3 times 10 to the 8 meters per second. What do you get if you do that? I get 1.3 times 10 to the minus 7. Hopefully you get that as well. Okay, now time dilation, if you write it out in terms of the boost, takes on a particularly simple form. T equals gamma T rest. Class, which time is the rest time and which time is the observer time? Can you tell in this problem? Who's at rest and who's the observer?
I think the students are at rest, and then the one moving is the other one.
Yeah, we have to be careful here. Why is the van time the rest time?
Oh, okay. I see.
It's 20 minutes according to the professor, right? The professor is like the train car with the laser beam. My watch inside the van is my tick-tock clock. The students are the scientists observers in the lab. So in this case, T rest. Do you understand that now, Arunsak? This takes the role of the observer in the train car, right? Okay. Okay, let's calculate our boost if you guys are capable of doing that. Gamma equals 1 over the square root of 1 minus 1.3 times 10 to the minus 7 squared. This becomes 1 over the square root of 1 minus, if I square that, I get 1.8 times 10 to the minus 14. Now your calculator is going to crap here, because watch what happens if you do 1 minus 1.8 exp minus 14. You get 1. Does that mean you have to give up? Now, obviously, the boost is going to be very, very close to 1. But what if we really wanted to calculate it? Can I show you a secret? Instead of doing 1 minus 1.8 times 10 to the minus 14, do 1 minus 1.8 times 10 to the minus 2. You get 0.982. Now make it 1.8 times 10 to the minus 3. You get 0.9982. Now do 1 minus 1.8 exp minus 4. Now at the 4th decimal place, you get an 8. That means 1 minus 1.8 times 10 to the minus 14 is actually going to be 1 over the square root of 1 minus 0. I need the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and the 14th will be an 8, and the 15th will be a 2. You could actually calculate a microscopic, oh, by the way, now you've got to play those same reindeer games to try to figure this out. Your calculator cannot handle that, but we can because we're smart. Let's do 1 minus 0.998. You get 2 times 10 to the minus 3. 1 minus 0.998. Oh, shit. Okay, this isn't going to work. Okay, fuck it. You know what? I'm going crazy here. You get a gamma of 1, right? Because 1 minus almost 0 is 1, and the square root of 1 is 1. There's virtually no time dilation. Why? Why is there no time dilation? What's my point?
Is it because you're not moving fast enough? You're nowhere near the speed of light, right?
Right. How fast do you have to go before relativity starts taking effect?
Dummy fast, like close to the speed of light.
No.
Fast.
I told the students the exact cutoff for relativistic regime, but they've forgotten, haven't you, students? You all forgot things.
20%, right?
Thanks. Devin knows, and so does Christopher. I want to share with you guys something. This might be a little too tech for you, but I don't want to believe that. Relativity, the boost. Sometimes they call it the Lorentz factor. I want to show you guys a plot. Oh, by the way, last time I noticed in the chat afterwards, I don't know if it was Devin, someone's like, are you going to talk about Lorentz transforms? I am talking about Lorentz transforms. That's what I'm doing. I'm just doing it in a sort of gentle kiddie kind of way. Let's see if we can find a plot of the boost. That's what I want. So images, hold on. The boost plot. Here we go. This is kinetic energy. There's a better graph. I did save it. Every time I save it, and every time I forget where, here we go. Well, this is sort of good. Let's open that in a new tab. This is a plot of the boost. There was this one really beautiful one that I love, which is so simple and elegant. And of course, I can't find that one because the universe won't be that kind to me. Oh, I can find it here. You will notice that the boost pretty much stays at 1 for speeds up to about 20% the speed of light. Unfortunately, this is a crappy graph. You actually do start to see some deviation above 20%. By the time you get to 50%, it's clearly noticeable. And after you get above like 80 or even 90%, the boost goes shitty bonkers, okay? That's where the times just start to get completely distorted and nuts, okay? Let's see what the chat says. 20%, yeah, okay. Listen, what if the professor could travel at the speed of light? Have you ever thought about that one? What if I had a speed of light ride from my house to CCRI? Let's try to calculate the boost then. Okay, so forget 90 miles an hour. The professor hits warp 1 on the Starship Enterprise and travels from CCRI to the classroom. Let's find the boost for V equals C. 1 minus the square root of 1 minus C over C squared. Okay, this is 1 minus 1. What is 1 squared? 1. What is 1 minus 1? 0. Becomes radical 0 is 0. No, Paul. That's what they told you in baby math class. In baby math class, they said, you cannot divide by 0. It is not allowed because your teachers don't understand what divide by 0 means. Of course you can divide by 0. You know what you get? You get infinity. Hold on, Cam. Hold on, Cam. If you divide 1 by a tiny number, 1 divided by 0.001, you get a big number, like 1,000. And if you divide 1 by 1 times 10 to the negative 10, a microscopic number, you get a macroscopic number. Sorry, this got a little messed up because I'm doing it backwards. 1 divided by 1 exp minus 10. I got to put the minus in afterwards. Wait. No, there we go. As you divide by a tinier and tinier number, you get a bigger and bigger number. If you divide by an infinitely tiny number, you get an infinitely big number. Okay, so what does time dilation mean then? T equals 0 times 20 minutes. Hold on, wait, did I do this right? Yes. Anyways, the result turns out to be this. This is the result that I wanted. The point is 0 seconds. If you can travel at the speed of light, you have an instantaneous journey from point A to point B. And that's true whether you're traveling 20 minutes to CCRI or you're traveling from the Andromeda galaxy to Earth. In the reference frame of a photon, time shrinks to 0. And I want you to contemplate what that means for a second. Let's take a peek at the Andromeda galaxy. I don't suppose any of you, I probably never told you. How far away is Andromeda? Does anyone know in light years? No one's going to know this. It's 2.5 million light years. That means the light that you see coming from Andromeda, it took 2.5 million years for those photons to reach your eyeball when you look at it through a telescope. But if you could surf on a photon, if you could travel at the speed of light, the time it would take you to go from the Andromeda galaxy to Earth, 0 seconds. In the perspective of a photon, time collapses in the direction of motion, which is pretty wild to think about. A photon is, the entire universe actually collapses to an infinitely thin sheet. Did I lose you there, Cam? Okay. Let's try this a different way. Could we redo the relativity problem that we did in our lab, which was the twin paradox? A pair of twins, brother A and brother B, travel to the nearby star system of Alpha Centauri. Now, I don't remember what numbers we used, but I know Alpha Centauri is 4.4 light years away. In it, we decided that, let's say the brother travels, I think we used 90% the speed of light. According to observer A, the distance traveled by A is the velocity times the time traveled by A. And the distance is 4.4 light years times the speed of light times TA, where the speed of light is now being measured in units of light years per year. How long does the trip take according to A? 4.4 divided by 90% the speed of light. Go for it. This is what we did last time. And what do you get? I only want to tell you this if someone's going to listen to me and think about it. Is anyone with me here? What's 4.4 over 0.9? This is bonus. I don't need to tell you this. I'm telling you this because it's cool. Thank you, Paul. What are your units, Paul? I don't see units, and I don't like it when you give me naked numbers. No. Light years over light years. You think it takes 4.9 seconds to get to Alpha Centauri? Sign me the F up.
.9 light years.
Light years are a unit of length, my dear. We need a unit of time. Thank you. Years. Sorry, but I had to point that out. 4.9 years. I understand why you made that mistake, but don't make that again. How long does it take observer B? Well, we have TA, the observer time is the boost, times TB. What did we say a boost of 90% was again? Didn't we say the boost was a factor of 2.3? Isn't that right? Someone, what do we get? Come on. My calci is dying here. Yeah. So if TA is 4.9 years, 2.3 times TB, how long does the trip take according to observer B? What the hell is that dog? What is that? Oh, it's a plushy football. Is that what? Or it's a.
It's a ball that he destroyed. He wants me to play with him.
Well, don't forget to play with me too. Here, we have calculation to do. To play with the dog. I don't stand a chance, do I? Okay, come on. TB equals 4.9 years over 2.3. What do you get? We got 2.1 years. And how did we understand that? We understood that the brother traveling at 90% the speed of light would experience dilated time and only take 2 years to get to Alpha Centauri. Now, here's the question. What if we did this whole thing from the point of view of the speed of light? There's something weird going on. I don't know what it is. At the speed of light, the boost is infinity. Oh, how long would it? Oh, right. No, it's not wrong. Actually, I've got this all perfect. This is good. How long will the trip take? Okay, this is what we did in lab last time. I got myself confused and then I got myself unconfused. Bear with me here. What if instead of 90% the speed of light, what if I made it the speed of light? And now I'm going to ask you the same question I'm going to ask you on the exam, so pay attention. How long will the trip take according to observer A? You should be able to answer this without any calculations. If V equals C, then TA will measure what?
It takes A 4.4 years.
Excellent. What about observer B?
Is it?
First, let's calculate the boost. The boost is 1 divided by the square root of 1 minus 1 squared. So the boost turns out to be what?
Infinite.
Good. So now we have 4.4 years for A equals infinity times TB. Solve for TB. 4.4 years divided by infinity. What does that give us? Cam, pay attention because I'm going to answer your question now. I just did it slower and more careful for you.
Is it still infinity?
No, what do you get if you divide any number by infinity? Think about this. Yes, Elijah. What does that matter? I mean, sorry, what does that mean? What does that mean? If TB says it's 0 years.
You got there instantly.
Instantly. So do you realize that, like they're lying to you in Star Trek? When they hit warp 1, there's no reason to go to warp 2 or warp 3 or warp 4. That's fucking stupid. If you go to warp 1, you get wherever you're going instantaneously. And by the way, it doesn't matter if it's Alpha Centauri or Alpha Cen, I'm at the end of the goddamn universe. It's irrelevant how long it is. The entire thing collapses to 0 seconds. That's what I meant, Cam, by if you could surf on a photon and you could travel from the Andromeda Galaxy to Earth, it might take 3 million years for our perspective. The light that we see is 3 million years old to us. But if you're that light, you got here instantaneously. Well, there's problems with traveling at the speed of light, Cam. let's learn about another aspect of relativity called length contraction. I do kind of need to move on from here. I'm going to, yeah, Mayo speed racing. Okay, can I erase here? Are we good? I hope you followed that, Cam. I did that for you. I wanted you to see that if the boost goes to infinity, that, by the way, earlier, can I make a correction in your notes? Earlier, I tried doing this, and after showing you that the boost was equal to infinity, I wrote down t equals 0 times tb. I screwed up there. Little man, I'm afraid what I'm going to see. No, I don't want to do that. Do I? Here. That's what I should have wrote earlier in the lecture. So please make that correction in your notes. I should have put infinity there, not 0. Do you guys know what I'm talking about? About a page back? Oh, you're all jacked up today. You don't know what the hell I'm talking about. All right, I'm going to erase this. Forget about it. All right. It's time to learn about length contraction. This is necessary for our homework today. Let's say, all right, so length contraction can be proved by a similar, hello? My mic, can anyone hear me? Raise your hand if you can hear me. Okay. Kaitlyn, everyone can hear me. Will someone chat her that?
I can hear you.
Sorry, have you lost audio, Kaitlyn? All right, well, figure it out. We can prove length contraction. Yes, you are they. Length contraction could be proved in a similar method to time dilation. You start with one observer, observer A, who's sort of standing at rest, and you take a second observer, B, and you put them in a boxcar traveling at some high percentage of the speed of light, okay? This time, however, what you do is instead of firing the laser from the bottom of the car to the top, you take the laser beam and you fire it the length of the cart and then bounce it back. As you travel at a faster and faster percentage of the speed of light, the path that the laser takes to get from the back of the car to the front of the car will slowly become contracted. Now, I can't take the time to prove it because when I did this last class, it took about 35 minutes. But I will tell you what the result is. The result is that for an observer B or for an observer A, you will see lengths in the direction of motion contracted by a factor gamma. Oh, yeah, like that. Or the way it's traditionally written is an observer's length will measure the rest length divided by gamma for a moving length. The idea is that the rest length of a ruler or a rod or a rocket ship, when you're in the same frame as that ruler, it will be 1 meter. 1 meter is the rest length of this ruler. But if this ruler were to fly past the classroom at 80% the speed of light, you, the observers, and me as well, would measure it contracted by some amount. I kind of have the perfect little cartoon picture. Oh, that doggy's doing the backstroke there. I like it. I have a perfect little picture to share with you to describe length contraction, which I think sums it up quite nicely. And it's this picture here. This picture imagines a rocket ship which is traveling first at 0% the speed of light at rest. And here it is with its rest length of whatever it is. It could be 25 meters or something like that, okay? This is the rest length of a rocket. As the rocket travels at successively faster and faster speeds, an outside observer will see the rocket contracted only in the direction of motion by a higher and higher percentage up until the point where they get to the speed of light, at which point the rocket will contract itself into nothingness. into absolute nothingness. Let's try a calculation with this. Oops, sorry, here you guys are. Okay, I'm gonna set up a legendary a problem called the barn paradox. Let's keep that handy. In relativity, this is known as the barn paradox. You guys will remember that we had two brothers who started their own spaceship company. And now they're taking their spaceship company to a space station in outer space. And there's a big floating platform. Brother A will stand on the platform inspecting the rocket as it travels past. Now, when they design the rocket, they design it inside the hangar, and they design the rocket ship to be the exact same length as the hangar bay. So let's put like a roof on this hangar. Okay, so here's the roof. And they're going to suspend the rocket ship from some cables while they work on it. Brother B is the pilot, so he's going to sit inside the rocket. And the rocket has the same rest length as the length of the floating platform, which is 25 meters, okay? So 25 meters is the length of the platform and the length of the rocket. That means the rest length in this problem is 25 meters. Now, however, Brother B is going to disengage the rocket from the straps, and he's going to accelerate, and he's going to blast past. Let's put the platform down here, okay? So this is the platform. And Brother B is going to blast past the platform at a velocity of 96% the speed of light. So they've improved the efficiency of their rockets since their company was founded here. Okay. As the rocket ship blasts past Brother A will observe a contracted length of the rocket. First, let us find the boost. Could you guys do that for me? What is the boost at 96% the speed of light? Thank you, Paul. Paul correctly gets 3.6. Paul, there's no units for the boost, so for once I'm not upset with your answer. What length will Brother A observe the rocket to have as it travels past? So what is 25 divided by 3.6? That should be very easy, right? Arunsak, can you use like
7
7 units? What are the units? 7 inches? 7 light years? 7 parsecs?
seconds.
Definitely not seconds.
Yeah.
This is a length, students, not a time.
Meters.
Yes. Okay. What will the situation look like from brother B's perspective, students? If I'm brother B and I'm inside the rocket ship, how long do I measure the rocket ship to be as I'm traveling at 96% the speed of light?
Would it still be 25 meters long?
Very good. For someone who didn't attend yesterday, Tuesday's lecture, you're catching on very quick. This is the perspective from brother A's viewpoint, right? Let's now draw the perspective from B's reference frame. I need to erase this. Everyone okay? I'm erasing. All right. From B's point of view, the length of the rocket as it travels at 96% the speed of light, actually, let's just get rid of that for a second, is 25 meters because brother B is in the same frame as the rocket. But now, guess what the platform looks like? Now, the platform, including brother A, has now shrunk to 7 meters. This is the perspective from brother B. This is the perspective from brother A. Do you guys see the difference? Okay. The essence of the barn paradox goes like this. Brother B travels through, now brother B believes the platform is moving past him at 96% the speed of light. Brother A thinks the rocket is moving past him at 96% the speed of light. In the barn paradox, here's what's happening. We get a set of garage doors that are controlled by remote control. And brother A takes a remote control receiver, and at the moment the rocket enters the barn, clicks the button and closes the doors on the barn to trap the rocket. Except in brother B's frame, that's not going to work. The barn doors will crash onto the rocket. What happens when brother A hits the switch? Does the barn doors close and trap the rocket successfully? Or do the barn doors crash on the side of the rocket? Which observer has the correct perspective? What makes it a paradox is both brothers' measurements are equally valid, provided that they're at a constant velocity, there's no accelerations, both things are true at the same time. In fact, the real dilemma to the paradox has to do with the fact that if you take a remote control and you fire the switch to close the barn doors will not close simultaneously for both A and B. This has to do with a more complicated aspect of special relativity called the failure of simultaneity. And it's the basis for our first homework problem today. And rather than try to draw it out on the board, which will take time, I'm going to show you a couple of animated GIFs to get you guys to think about it. Let me share with you a couple of crappy cartoons. Imagine a platform, slide 34, in which two observers are watching an event take place where photons, an A photon and a B photon, are fired from two flash bulbs to strike an observer at the center of the platform. This cartoon is seen from the center of the platform's reference frame, the observer on a platform. And here at the bottom is some dude moving past him at a high percentage of the speed of light. According to the observer on the platform, the photon flashes A and B are simultaneous, meaning they're at two different coordinates, they flash at the same time, and both photons hit the observer at the same time. What will this cartoon look like from the reference frame of the moving observer at the bottom of the frame? Let's take a peek. Something totally different is happening. Both observers need to agree that the two photons strike the man on the platform at the same time. If both observers have to measure the same speed of light, there's only one way that can happen. According to the observer on the ground here, the flash A needs to go off first before flash B so that it has time to catch up. The meaning of this is that for an observer here, if one observer in one frame sees two events as simultaneous, an observer in a moving frame relative to them will not see those events as being simultaneous. This is known as the failure of simultaneity. And it matters for us because sometimes this can take the form of you're in the Milky Way and there are two other galaxies far away from you. If we see two supernovae go off in those galaxies at the same time, usually those galaxies are moving with respect to you. Those supernovae will not happen at the same time in those other frames. It's a little bit complicated and it's hard to explain it in about 2 or 3 seconds. But this thing called the failure of simultaneity is something that we're going to address in our class today. I think this stuff is really cool too, Cameron. I'm interested in weird, surreal stuff that's hidden under our noses. Okay, I didn't get to all the other aspects of special relativity, but I'm going to take 2 or 3 seconds now to just have a quick discussion. Well, you know what I might do? I'll probably run, you know what? Here's what I'm going to do. Next week, we only have one class, right? Tuesday. And we have no homework next week because of Thanksgiving. Rather than smush general relativity into 2 minutes, I'm going to just burn a class. And our next class before Thanksgiving, I am going to focus on general relativity instead. So does that seem like the right thing to do? It means we'll get a little less far in the class, but I think that means it won't be rushed. I indulged myself. I really like this stuff, so I spent a long time, but I was also doing it for a reason. On the exam, I am going to make you do problems in both time dilation and in length contraction, and I am going to make you calculate the boost. I'm not even trying to hide it from you. Yeah, why wouldn't we have class on Tuesday? Oh. CCRI
One of my
says,
other classes does, and I wasn't sure if it was all of them.
that's because them's lazy folk. Them's lazy folk that don't know the value of hard work. But luckily, we ain't like that in
The
this
value
class.
of money.
Say that?
Don't know the value of the money I spent for the classes.
Exactly. See, I'm giving you your maximum value, Kaitlyn. I like to supersize your value meal here. Okay, so we will have class on Tuesday, but maybe it'll be like a fun class where we talk about stuff. I don't know what I'm going to do for the lab yet. I have to decide that. Who knows? Anything's possible. Okay. Okay, Arunsak. Mine too, actually. That's why I'm glad I'm stuck in it forever. Okay. Why don't we take our break now for once? For once, I'll actually end on time. And we'll do our homeworks. We do have a relativity homework to do. So we'll start that at 1:10 Does that sound like a plan? Okay. So take a little break. I'll see you in 20. All right. It's time to get to homework number 11. This covers 3 different chapters from the book. There's a few questions from chapter S2, which is special relativity. 1 question from S3, which is general relativity, but that's okay that we haven't got to that yet. And then 1 question from chapter S4, just on the measuring the strength of gravity versus electromagnetism. So hopefully you guys can call those numbers up. They should be under the, excuse me, the homework tab. Where are we here? Under the homework tab. Should say number 11. Okay. So 47, 51, 53, 59, 52. Let's see if I can remember that. Because we spent so much time training with the boost and with those formulas, I'm guessing this is going to be a short and easy homework. At least that's what I think. So, as usual, put your nomen up at the top of the page. Astronomy 1020 with your section, of course. And then this will be homework number 11, chapter S2, 47, 51, 53, 47, 51, 53, chapter S3, 59, and chapter S4, 52. Okay, Christopher Leonard, you're first in my Hollywood Squares today, so chapter S2, 47. Get yourself ready to read it, Christopher. Meanwhile, hold on, I gotta take this tea bag out so I don't oversteep my tea. That's the first order of business. Second order of business is in order for us to understand the problem that Christopher's about to read to us, we have to understand that in the book that nobody reads, which is the textbook for this class, there is an example called Thought Experiment 8. And I want to lay this out to you. Thought Experiment 8 has to do with the title of this problem, something called the failure of simultaneity, the failure of simultaneous things. And I believe the setup is that there are two spaceships. And for the purposes of argument today, we're going to just imagine that these spaceships are square, okay? Oh, that's a good use for your textbook, Christopher. You are in the bottom spaceship, and there's an intrepid space explorer named Al who's in the top spaceship. And Al is moving relative to you at some rapid velocity. I don't know if they specified it or not, but let's imagine it's 90% the speed of light for argument's sake. The length of your spaceship is identical to the length of Al's spaceship. The only difference is that Al's spaceship has some blinky lights on it. I believe there's a red blinky light on the right side, and there's a green blinky light, I'm sorry, on the left side, and there's a green blinky light on the right side. The setup of the experiment is as follows. At the exact moment when Al's spaceship passes you, at that exact instant in time when your two spaceships are lined up, you see both bulbs flash simultaneously. In other words, the bulbs are clearly attached to Al's spaceship, but a red flash goes off, and you see the red flash go off simultaneously to the green flash. So you see the flashes as simultaneous. Now, let's see if you can understand thought experiment 8 before I explain it to you. Let's see if you followed this from lecture today. And trust me, I'll forgive you if you didn't quite get the point. Is Al going to see both of those flashes simultaneous in his frame? Yes or no?
I'm gonna throw out an educated guess and say no, he doesn't see the same thing.
That is correct, because as you learned in
It's either
today's
red
lecture,
first.
simultaneous in one frame means it cannot be simultaneous in a moving frame. Now, Kaitlyn, you've already done good. Can you answer the next question? If they are not simultaneous, Al is going to need to see one of the flashes before the other. Can you tell me which flash he sees first?
I'm gonna go out on a limb here and I'm gonna say it's the red one.
No, it's the green one.
Cool,
Let's,
green's better anyway.
let's slow down time here and let's understand why. Do you agree with me that Al is moving in the direction of the green flash? Let's just start with that simple proposition. You agree that Al's moving towards green. You also agree that both observers need to measure the same velocity for the speed of light, correct? This means that in order for Al's ship moving like so to have both photons hit you, Al needs to see the green photon flash, the green bulb flash first, so that, because you're from, let's think about this from Al's perspective, Kaitlyn. From Al's perspective, Al believes that he is stationary, okay? And that there's a green flash here, and there's a red flash there. Al also believes that you, not him, are moving past him at 90% the speed of light, and that you are moving to the left, right? You got to go through this real slow now. If you are moving in the direction of the red flash, and you see both flashes simultaneous, from Al's perspective, the green flash has to go off first to travel the slightly longer distance to hit you, and the red flash has to go off second because it doesn't have as far to travel before it hits you. In other words, in Al's perspective, he's going to barrel into the green flash before the red flash. From your perspective, the flashes are simultaneous, but Al's in the middle. Al will be racing toward the green flash, and it will take longer for the red flash to catch up to him. Hopefully you guys can understand how both of those scenarios both result in you getting flashed at the same time and Al getting flashed with the green before the red in both scenarios. The laws of physics are the same in all inertial reference frames. All observers need to agree that both photons hit you at the same time. All observers need to agree that Al is hit by the green photon. And now we are ready for Christopher Leonard to read us question 47. Oh, by the way, let's label these for everyone's convenience. This is your view. This is Al's view. Christopher, anytime.
Hi. 47, right?
Please, S2.
Eh. Which one's the thing? Right, relativity of simultaneity, whatever the fuck that is. Consider the situation in thought experiment 8 about the green and red flashes of light at opposite ends of Al's spaceship. Suppose your friend Jackie is traveling in a spaceship in the opposite direction from Al, Further, imagine that she is also precisely aligned with you and Al at the instant the two flashes of light occur in your reference frame.
Okay, now we're going to answer some questions. Read them very carefully, Christopher, because the words matter here.
What are the questions?
Like part A, right?
It could be.
The page cuts off there.
Yeah, you gotta go to the next one.
Ugh. A, according to Jackie, is Al illuminated first by the green flash or the red flash? Explain.
From Jackie's view. All right, who's brave enough to answer? Class, what does the scenario, this is your view. In your view, Al moves to the right and Jackie moves to the left at the moment you're aligned. Can you guys imagine what it would look like from Jackie's point of view? What would it look like from Jackie's point of view? Arunsak.
I think that so the other person would always be moving in the opposite direction, but they're both moving away from each other. They're just gonna move faster away from each other.
Wait. Hold on. You need to say this better. You need to complete your speech. From Jackie's point of view, is Jackie moving?
Jackie is not moving.
Exactly. That's the starting point. So according to Jackie's point of view, she's at rest. Which direction is Al and you traveling in, right or left?
Al and you is traveling to the right.
With Al traveling a bit faster than you, probably.
Sure.
Okay. Cameron, be careful. The question did not ask which flash will Jackie see first. The question asked, according to Jackie, which flash hits Al first. That's not the same question, Cam, that you answered.
It's the green one.
Yes, how do you know?
Because Al and you, or this is asking Al. Al is moving towards the green one.
That's right. According to Jackie, Al is hit by the green flash first. All observers need to agree that Al is illuminated by the green flash first. Okay, Christopher Leonard. Do you understand, Cam? You were answering a different question, Cam. The wording here is subtle. Okay. Christopher, take us down to part B. Wait, hold on, Cam. Do you want me to explain that a little better? Can I explain a little better what happened there? Because you may not understand what happened there.
I thought that since Al is moving to the right, that the red flash would have to go off first, since it would have to travel that.
Wait, the red flash would have to go off first according to whom? Every observer has a different, according to whom?
I thought according to Jackie.
That is correct. I'm not saying that's wrong. Clearly, if you see the flashes simultaneous and you see Jackie moving to the left, the red flash is going to hit Jackie before the green flash catches up to her. This is what I meant by you were answering the wrong question. You were answering the question, what flash does Jackie see first? That was not the question. The question was, according to Jackie, which flash will hit Al first? Now you're making the mistake of assuming that if Jackie sees the red flash first for her, that she'll have to have Al see the red flash. That's not how it works. Jackie can see the red flash go off first, then she can see an Al illuminated by green light, and then afterwards she can see Al illuminated by red light. Do you understand now? That's what I meant by you were answering the wrong question. You were answering the question, according to Jackie, which flash does Jackie see first? The question was actually, according to Jackie, which flash does she see Al see first? It's a little tricky here. They don't have to be the same thing. Did that help? Whoever you were, I was just
Yes.
talking.
Yes,
Okay.
thank you.
Okay, good. I want to make sure I won there. Okay, so let's go to B. Christopher.
According to you, which flash illuminates Jackie first? Why?
Okay, so whoever I was just talking to, do you want to try this one to see if you get it now? Which flash hits Jackie first?
Red, right?
That's right. All observers agree that the red photons will hit Jackie before the green photons do. Jackie interprets it as the red flash went off first. The rest of us interpret it as Jackie barreled into the red photons first. Please write this down before we continue because I need to erase A and B to write C. It's a bit more lengthy. Devin, that must be an internet connection issue. Is that better, Devin? I can only hold this so. Devin, you let me know when you're done. Okay. We quirky? Are we quirky? All right, I'm erasing these two parts. I don't like this. Christopher, take us away.
See, according to Jackie, which flash occurs first? Explain. How does Jackie's view of the order of the flashes compare to your view and to Al's view?
Basically, they're asking us to do 3 mini questions in once. They're asking about the order of events from all 3 perspectives. From all 3 reference frames. So there's Al, there's you, and then there's Jackie. From each of your perspectives, describe the order of events. Let's start with Al. Class?
Is the first one for Al, he sees us hit by green first?
No. This time we're just asking about the flashes from each of your perspectives. This isn't what does Al see you, this is what does Al see in terms of the sequence of flashes.
Oh,
So in that case,
so green first?
then red. Okay, how about you? What do you see?
Same time.
It's very Christmassy today.
Yeah, I know. I was thinking about that. It's time to get in the holiday spirit. And then how about Jackie?
Red first.
Nice. Some holiday cheer there. And that takes care of problem 47. Just give a second for anyone who's catching up. Oh, I'm so pleased with myself. Okay, can I erase? Who's next? Kaitlyn. Kaitlyn, could you do us 51, please?
Absolutely. Let me pull that John up. Bear with me one moment.
Uh-huh.
What number was it? 50?
Sorry, number 51 in chapter S2. It's kind of blurry for me too. What's going on here?
Oh, wait, hold on. Why is this not here? 51. Okay, here we go. Length contraction. Marta has a spaceship that measures 50 meters from end to end when at rest. If she flies past you at 0.75 speed of light, how long will you measure it to be? Oh, that was part A. Do you want me to read B too?
No, let's start with A. Let's remember the formula for length contraction. The observed length is the rest length divided by the boost, where the boost is defined as 1 over 1 minus V over C squared. In part A, we have a spaceship with a 50-meter rest length. We have a velocity of 75% the speed of light. Watch this little trick. If I substitute in gamma for there, you'll notice that gamma is on the bottom. That's going to flip this square root up to the top. So the equation actually looks like this. L equals 1 minus V over C squared times L rest. So can you guys tell me how to do that there? Let me see if I can make that neater. So tell me what to write.
That would be.
Oh, you already did it. Someone typed the correct answer. Was that Arunsak? I can't remember who. So that's your setup. 1
It
minus.
was Cameron.
Oh, sorry, Cam. 1 minus 0.75 squared. And Cameron, I believe, has the correct answer of 33 meters. Did you guys all get that? Okay, sorry, dude. Handwriting is bad today. Squat up. And then Kaitlyn, when you're ready for B. Nasty over here. There's a lot of gick. Gick everywhere.
Okay, and part B. The star Sirius is 8.6 light years from Earth in our Earth-based reference frame. Suppose you traveled from Earth to Sirius at 0.92, what is that, speed of light? 92% speed of light, I think that is. During your trip, how far would you measure the distance from Earth to Sirius to be?
So it's 8.6 light years away. Your velocity is, I'm sorry, it was 92, did you say?
Yeah, hold on. Where did that go? Yeah, 92.
All right, so what do I do, gang? What do I do? Say what you say when you do what you did to me, okay?
Are you talking to me?
Well, I was just kind of quoting an old 70s song, but
Oh, never mind then. Sorry.
everyone's head there, I guess. Did anyone get that reference? No. Stacy got it. Okay. Squat up, all right? Or gang, or whatever you guys say. I can't speak LOL with these kids here. Okay. Anyways, I just want you to, Kaitlyn, fine, I'm talking to you, Kaitlyn. What should I write down?
You're asking the wrong person.
No, this is
I
so simple. It's just a length contraction problem. If you stop and slow down and think, you know how to do this. Psst.
Okay.
What we did in part A, okay? Just do the same thing.
Oh, okay. So, is it like L equals the square root of 1 minus 0.92 C squared?
Hold on, not C. Why is it not C squared? You need to understand this. This is important.
Because you don't need the C.
Because it's V over C. V over C is just 0.92, right?
Yeah,
You agree with me, correct?
100% I agree.
All right, okay. And then what am I multiplying it by?
8.6 light years.
Good. Okay, so now do that. Was that the name of the artist? Is that Cameron that?
Made of that 70s show reference earlier, but nobody caught up.
Oh, sorry. No, that's Jermaine Jackson. Is that Jermaine? Yeah. Everyone forgets about Jermaine, but he was awesome. Okay.
3.4 light years.
That's kind of cool because if we could travel close to the speed of light, the distances to the stars will contract and we could get to our neighborhood solar systems faster and easier and cheaper. We could consort with aliens.
Is that even possible to get like humans near the speed of light? Pretty much impossible, right?
In theory, it should be. One of the problems that we didn't get into was the equation for mass increase is the same as time dilation. So what happens, Arunsak, is as you get closer and closer to the speed of light, the mass of the moving object will grow towards infinity. And because the mass increases close to the speed of light, the energy required to continue to accelerate you goes to infinity. The problem is that as you get, so in theory, Arunsak, we could get closer and closer, but the closer you get to C, the more technologically impossible it becomes. It would take an infinite amount of energy to accelerate to the speed of light. However, this proves, Arunsak, we don't actually have to get to C. We could get to some high percentage of C, and we would significantly reduce our travel time, right? That's exciting. Okay, I'm done with this. If you're done with this, don't give up hope. Don't get, alien boyfriends are out there waiting for you, okay? All right, so let's, can I erase this? Are we good? I'll assume that's a yes. Okay, Arunsak, are you down to read us a problem there? Like chapter 2, number 53?
Yeah, is my mic too high? Is there a lot of noise?
No, it sounds fine, bud. Sounds absolutely fine.
All right. Get back. Question 53.
Yeah.
Section 2. All right, the title is Time Dilation with Subatomic Particles. You ready?
Yep.
All right, a pi.
That's a
plus,
pi meson.
Okay, a pi meson produced at rest has a lifetime of 18 nanoseconds. Suppose a pi meson is produced in a particle accelerator at a speed of 0.998 c. How long will scientists see the particle last before it decays? Briefly explain how an experiment like this helps verify the special theory of relativity.
This is really important because this happens all the time in the Large Hadron Collider. Someone was just asking me, is it theoretically possible for us to get to the speed of light? The lower the mass of the particle, the easier it is to accelerate them to such outlandish speeds. You may not realize this, but we accelerate subatomic particles up to speeds like this in the Large Hadron Collider all the time. Usually what happens is you have a scientist, okay? And the scientist is in the laboratory frame, okay? And he's accelerating the pi meson on some kind of a track, and he's zipping it around the Large Hadron Collider. The scientist has a clock. This clock is the laboratory frame. There is also a reference frame that travels along with the pi meson, like you're surfing on the pi meson, and that's the pi meson frame. They tell us that the pi meson has an 18 nanosecond rest time. And remember that the formula for time dilation is the observer time is the boost times the rest time. My recommendation on how to solve tricky problems in relativity is why don't we first calculate the boost, which is one thing, and then we'll worry about who's the rest frame and who's the other frame. So should we calculate the boost first? I think that's a great idea. So the boost is 1 divided by the square root of 1 minus 0.998 squared. And Kaitlyn, this is important because I see people do this all the time in the exam. That's not 0.998 c squared. That's just 0.998 squared because the c's cancel out. You'll remember that, right? Okay, good. And I want everyone else to remember that too. I ain't just talking to her. Get me my boost. Stacy, can you give me the boost? Let's have Stacy do it. No, come on, Stacy. Stacy, the point of this is our training time. Most of you are not going to study for the exam. I already know that. That means whatever we do now is our study time. So let's make sure if you can't do it with me here, you can't do it on the exam. Try it. Tell me what you get. If it's wrong, we're going to work through it.
Okay.
I'm guessing there's more than a few night students that will benefit from seeing it punched one more time.
Yeah, I apologize. I got 0.0632, which I
Okay.
know is,
Yeah, that's not right. The boost has to be a number greater than 1. Okay. Follow along with me, Stacy, and everyone else. Stacy, we're going to do inside first, then we square root, then we reciprocal. Okay. So watch me. 1 minus 0.998. We have to square that. So hit square. Now we have to hit equals to do the 1 minus. Now we square root. Shift, square root.
that's where I stopped. That's where I went wrong, because that's, yeah.
Then we have to do the reciprocal. So watch, Stacy. Shift 1 over x. All right, we all got 15.8. Nice. Stacy, that wasn't just for you. That's because I suspect the people who watch the class later, they might get confused and not be able to say, hey, wait, how did you do that? So that was just for everybody.
Thank you, I appreciate it.
Professor,
Yes.
which one is the 1x key?
Yeah, hold on.
The one that looks like parentheses, kind of?
The close
Yeah.
parentheses.
Yeah,
Yeah,
yeah.
hit shift first. Shift close parentheses.
Okay.
Is 1 over x. Okay. So now let's talk about the 18 nanoseconds. Which t is the 18 nanoseconds? No tricks.
The one in the equation on the right.
The rest time.
The rest one, yeah.
Notice my symbolic use of colors. That was the observer B in our cartoon. So now we will calculate the observer time frame is 15.8. Notice we can keep the same units of nanoseconds. We don't need to convert. Times 18 nanoseconds.
Professor, I got a question.
Yeah.
So on like an exam, is there any time where we do have to divide by the speed of light constant, or can we just ignore that overall?
I suppose if I gave you a velocity in meters per second or in kilometers per second, then you would have to divide. But as long as you're getting the speed of light as a percentage of the speed of light, then you're cool. Look at that doggy. Look at that happy doggy.
What is
Dog's an oaf, sorry.
No, I love it. You looked like you were having fun, or somebody was having fun. We were having fun just watching
He's
it.
having a good time.
That science love dog. Arunsak, I'm sorry, you were going to ask me a question.
You answered it.
I answered it, right. Sorry, I got distracted there. What's the answer to this guy?
Somebody else asked you a question though.
Oh, what was it?
I was gonna ask what the unit is after 18.
Oh, nanoseconds.
Oh, nano. Okay. I was like, wait, what is NS? I couldn't figure out what it was. Thank you.
Sorry, that's the standard abbreviation for nanoseconds. Nanoseconds are 10 to the minus 9 seconds. Okay, that's too many sig figs, Emily. Let's do, Emily, we've got 2 sig figs here, so we'll keep 280 nanoseconds. Now, Arunsak, there's another part to this question.
Okay, go read it.
Yeah.
Let me write this down real quick. No, there's not another part.
Read the question again.
Yeah. Briefly explain how an experiment like this helps verify the special theory of relativity. That's the second part.
Do you guys understand what they mean by that? Arunsak, you were talking about proof or about, yeah. Go ahead, Arunsak.
My guess would be is that when you go to this small of a scale,
No,
the rule doesn't apply.
Forget about small. It's about time.
Okay.
Stick to time.
It's too small of a time.
Well, what's too small of a time? We can measure 18 nanoseconds and we can measure 280 nanoseconds. False. It's not too small of a time. Not too small for a professional.
Then I don't know how to answer that question.
All right. You guys need to understand that this is referencing a famous experiment that is considered one of the key supports of relativity. And you know where it was conducted? Right up the street at Mount Washington in New Hampshire. You guys may have heard of Mount Washington being famous for some of the worst weather on planet Earth. They have a science research station up there where they measure particle collisions with the atmosphere. Okay, so probably no one's told you this before. Let's draw a picture here of Mount Washington, okay? And here's our atmosphere, which is made of nitrogen and oxygen molecules. There are these particles that come from supernova explosions in deep space. They are known as cosmic rays. And some extremely high-speed protons traveling at almost the speed of light will fly through the galaxy after being emitted from a supernova, and they strike our upper atmosphere and create basically a little nuclear explosion, which makes a shower of subnuclear particles like pi mesons. And there are scientists that have a base up at the top of Mount Washington, and they measure these particles with a Geiger counter of sorts as they strike the upper atmosphere. Some of the intensities of these nuclear explosions rival the Large Hadron Collider. This is how we discovered things like pi mesons. We discovered that pi mesons will only live for 18 nanoseconds before they spontaneously decay into something else. They transform themselves. So you can think of it as the shelf life of a pi meson is 18 nanoseconds. 18 nanoseconds is such a short period of time that even traveling at the speed of light, the pi mesons should decay and disappear before they make it to the bottom of the mountain, which is why no one had ever noticed them before until they made a station up at the mountain. They were close enough to the top of the atmosphere to get the sparks. Well, lo and behold, some intrepid scientist who was thinking about relativity decided to build a detector at the bottom of the mountain. And sure enough, even though it was in theory impossible, some pi mesons started making their way down to the bottom of the mountain and getting registered by the detector. They couldn't figure out why until they realized that traveling at the speed of light meant from the frame of the pi meson, the mountain was actually undergoing some length contraction and was shorter than it should be otherwise, the pi mesons didn't have to travel as far to get to the base of the mountain. This was considered a confirming test of relativity. Another way to look at it is this. From the point of view of the laboratory frame, in our problem, from the point of the laboratory frame, we know that a particle that lives 18 nanoseconds, if it suddenly is measured to live for 280 nanoseconds, that should not be possible according to the laws of physics, unless the particle is undergoing time dilation. In other words, the fact that you see the particle live so long is proof that time dilation is real. It's another version of the Hafele-Keating experiment. Let's write the following sentence. By observing a high speed particle live to 16 times its natural, let's say, lifespan, to make this. By observing a high-speed particle live to 16 times its natural lifespan, we see evidence of time dilation in action. That's the only point. The point is, seeing a particle live to 16 times longer than it should is evidence that time dilation really does happen. Is 0.998% the speed of light a high speed? What if, Arunsak, just to blow your mind for a second, I want to show you something here, buddy. And it's not Jermaine Jackson, although that's cool too. Large Hadron Collider. Wiki. Where is it? What does it say are the speeds typically reached in the Large Hadron Collider? What does that say, Arunsak?
Almost the speed of light, very close.
In fact, they even give you the Lorentz factor, which is another name for the boost. At 0.999999990 C, your boost or your Lorentz factor is a factor of 7,000. That means they experience a factor of 7,000 time dilation. And by the way, Arunsak, that's what makes the nuclear explosions so powerful, is because of mass increase. When they slam the two protons together, they're not just slamming two protons together anymore. The masses of each proton have grown by a factor of 7,000. It has the equivalent energy of slamming 7,000 protons together. That's what makes the shower of nuclear particles come out, like neutrinos and stuff. That's what they're doing.
How is it not just blown up?
Well, because these particles are so light in terms of their mass that though they do create energetic explosions, the energies are still measured in the electron volt range. They're not enough to create a nuclear reaction or something like that. Now, if you could do that with, you know, a huge stream of plasma all at once, that would be a different story. But remember, it's still only single particles. A cosmic ray could hit your forehead and make a nuclear explosion in your forehead, and you wouldn't even feel it because it's just one proton, right? You are much more massive than a proton. All right. Stacy, can you read us chapter 3? That's awesome. Could you read us chapter 3, number 59? I'm erasing this, by the way. If you have any objections, speak now. Mind blown, literally true. True. I love it.
All right. Gravitational time dilation on Earth.
All right.
Early-
Hold on a second, Stacy. Stacy, before you continue, I need to show everyone a picture. You will remember that in today's lecture, I told the class that general relativity is a more expansive theory of gravitation. It turns out that some of our friends from special relativity are going to show up again in general relativity, but this time they'll take the form of some kind of a weird effect of gravity. One of the most famous is an equation called gravitational time dilation. Gravitational time dilation says that clocks will run slow in the presence of a large gravitational field, such as a black hole or a neutron star or something like that. Usually you're comparing two clocks, one of which the rest time is usually at the, well, let's see. The observer time is usually far away in deep space. The rest time is the time of a clock sitting on the ground. And you see a factor that looks a lot like the boost here. It's 1 divided by the square root of 1 minus something over c squared. Believe it or not, guys, you have seen this formula before. Does anyone know what 2gm over r is? I don't suppose you remember that from our lecture 4, do you? Lecture 3, maybe? Does anyone recognize that term or that factor 2gm over r?
It looks familiar, but I honestly don't remember what it means.
This is the square of the escape velocity. Remember escape velocity? That's the square. So instead of 1 minus v over c squared, it's 1 minus escape velocity over c squared. Kind of clever. The meaning is that clocks, by the way, last class, I reread the chat after class, and someone had been talking about the movie Interstellar, which I have my own beefs with. But if you saw the movie Interstellar, you got to see gravitational time dilation. Okay, Cam, remember when he goes down to the surface of that planet that's near a black hole, and like every second he spends on the planet is like hours and hours or days and days outside?
No. It was every hour he spent there was I think 4 years back on Earth.
Okay, yeah, something like that. But he was experiencing this. This is gravitational time dilation. By
Wow.
the way, one of the consultants for that movie, the science consultants, was Kip Thorne, who is the world's foremost expert in general relativity. So they consulted like the man in general relativity. In Kip Thorne is considered to be one of the preeminent scientists whose specialty is studying general relativity. He teaches at the legendary California Institute of Technology, aka Caltech. That's like the MIT of the West Coast. Legendary school. Okay, now let me write down the gravitation. Let's set it up before Stacy reads the problem. So in the problem, we are going to have a massive object. Was the problem about the sun or about Earth, Stacy? Stacy's lost here. Let me see if I can see what the problem's all about. Lost Stacy in the way. The problem, this out of the way here, chapter S3. '59. It's on Earth, okay? So here's Earth. Earth has a radius r sub Earth. And we're going to have two clocks. One clock is at the surface of Earth. And this clock is typically called the rest clock. And then somewhere out in deep space is a second clock. We call this the observer clock. And the formula is the observed time is the rest time over the square root of 1 minus the escape velocity over the speed of light squared. Okay, sorry about that long ass intro, but now we're ready for Stacy to read us the problem.
Okay. Okay. Gravitational time dilation on Earth. For a relatively weak gravitational field, such as that of a planet or of an ordinary star, the following formula tells us the fractional amount of gravitational time dilation at a distance r from the center of an object of mass m object.
Okay, I forgot. They're not going to have us use the official formula. They're going to have us use the fractional amount of time dilation. That means the change in time over the observer clock, I believe, is, and what's the formula? It's like 1 over c squared.
C squared times gm object over r.
And by the way, what they mean by fractional time dilation is the difference as a fraction of the observer clock, I believe. Okay. Once you've got that down, Stacy, you can continue reading.
Oh, sorry. Okay. All right, it's got a long equation in brackets. Do you want that?
Is that what we just wrote down?
No.
What's
It's G equals 6.67.
Oh, that's not an equation. That's a number. That's
number,
the
I'm
value
sorry.
of G. What did they give us for the value?
Values. Okay, so the value of G is 6.67 times 10 to the negative 11th m squared.
Those are units, not variables. Meters
I'm sorry.
cubed per kilogram per second squared. That's just big G. We usually know it as 7 times 10 to the minus 11, but
Okay, and then that's over kilograms, inside brackets, kilograms times s squared.
Yeah.
Okay, fine, then I'll skip the rest. All right, for example, when 1 hour passes in deep space far from the object, the amount of time that passes at a distance r is 1 hour multiplied by the factor above.
that's
And
not
then in
strictly true. They lied there, but okay. It's the
And then
difference.
in parentheses, it says this formula does not apply to strong gravitational fields like those near black holes.
Okay, so what does it want us to do?
It wants us to calculate the amount of time that passes on Earth's surface while 1 hour passes in deep space.
Okay, so here the observer clock is 1 hour, and they want us to calculate the rest time. This is going to be a wee bit tricky. So here, the R is going to be set equal to the radius of Earth. That way we can calculate the fractional time dilation here versus there. Okay? So we have the radius, the mass of Earth is 6 times 10 to the 24 kilograms. The radius of Earth is 6,400 kilometers. Class, how many meters is that?
64,000.
All right, you fail. Let's try to do it with dimensional analysis.
640,000.
How many meters per, well, sorry, let me try that around. How many meters per kilometer?
1,000.
So try again. It's not 64,000.
640,000.
It's not, use a calculator. $6.4 million meters. Apparently, we still need dimensional analysis in our lives. All right, so let's figure this out. Our change in time divided by 1 hour is equal to 1 over 3 times 10 to the 8 meters per second squared times I need to erase some of this. Do you guys have this? I got to erase that. Ow. Times 6.67 times 10 to the minus 11 meters cubed per kilogram per second squared times 6 times 10 to the 24 kilograms divided by 6.4 million meters. Okay, that looks like a U job right there.
I got 0.2. This is definitely wrong.
I got times 10 to the negative 10.
I got 0.2 also.
All right, Jesus Christ. Here we go. 1 divided by 3exp8 squared equals times 6.67 exp negative 11 times 6 exp24 divided by 6.4 exp6. Christopher was right. 7 times 10 to the minus 10. I'm going to be writing this up here now. This next part's going to get tricky. The change in time over the observer time is T. Let's see, wait a minute. if clocks run slow, their time is shorter. So it's t minus t rest on the Earth divided by t. And the t is 1 hour. 1 hour minus t rest divided by 1 hour is 7 times 10 to the negative 10. What are the units of 7 times 10 to the minus 10? Christopher, you were good enough to get it on the first try. Can you tell me the units?
Hours?
Hours are on top and bottom on this side, but that's not ours. If that was that Gabby or who was that? Was that Gabby? That was somebody.
No, that was me.
Oh, sorry. I think it was just your voice got distorted somehow.
No,
Gabby's in the other class. There's 2 classes, guys. I'm starting to get you guys mixed up.
my
Okay,
brain
look.
is melting.
Meters squared times a meter is meters cubed. Meters cubed cancels with meters cubed. Kilograms cancel with kilograms. Seconds squared cancel with seconds squared. What are your final units? Huh? Can I tell you what it's like, what I hear on my end? I say, what are the units? And let me tell you what I hear. That's what I hear, okay? I hear, psst. I don't know what to make of that.
Hours,
No,
meters, seconds.
We already tried hours.
figure it out while I turn the heat down a little bit.
Did he just say it wasn't years?
I don't know.
Guys,
Hours per second? That doesn't even make sense.
what do you mean it doesn't make sense?
Hours per second?
On the top, you have meters cubed per kilogram per second squared times a kilogram. On the bottom, you have meters squared per second squared times a meter. What cancels?
Okay, the second squared.
The squared?
What else cancels?
The meters?
Yeah, because meters cubed cancels at meters cubed.
Kilograms?
What are my final units?
Nada. Nothing.
Exactly, because it's a fractional time dilation. It's what percentage of an hour? It's a percentage.
You sneaky snake.
Uh-huh. I wanted to see if you guys could do that. Unit canceling is important. That's a version of dimensional analysis, by the way. I'm glad we had that talk. Okay, you're not done yet. Do you see what your problem is? You guys have to solve for T rest. That's not as easy as it looks at first. I'm going to erase this stuff at the bottom. Okay, follow along with me. I'm going to multiply the 1 hour times 7 times 10 to the minus 10. 1 hour minus T rest is equal to 7 times 10 to the minus 10 hours, because I basically just multiplied it by 1 with some units. That means T rest is 1 hour Can anyone actually get that for me? What happens when you punch it into your calculator?
I get 1.
All right. Let me show you how to do this right. You ready for this, Christopher? We can't plug this into our calculator, but we can plug similar things. Let's see if you guys can follow the pattern with me.
Like I get 0.9 a bunch of times until a 3 comes.
Exactly. Oh, until you get a 3 come out. How many? Yeah. Let's get the right thing down. How many 9s do you get?
Oh God. 1, 2, 3, 4, 5, 6, 7, 8, 9 9s.
Your calculator can handle that. What does this mean, Stacy? You know what the news was doing? The news was coming up with this bastard analogy that when they had the twin brothers, one of which went to the International Space Station, they uglified it by calling it the twin paradox. Twin brothers ISS. I don't remember where it was, but they called it the twin paradox. But now tests, fine. Test on astronaut and twin brother highlights space flight's human impact. They had 2 brothers, one which was on the ground, the other that spent some time on the International Space Station. Now, I don't know where, but I saw some media organization call this the twin paradox, and it irritated me greatly. Well, whatever. The point of the problem is, oops, where are you guys? Is there any difference between the passage of time on the International Space Station versus on Earth? I mean, effectively no, and yet Arunsak, with a sensitive enough chronometer, you could actually measure those differences, right?
Did you ask something? My audio cut out.
How many of you use this for GPS when you're driving around? Pretty much all of us, right? Do you know how they do that? Do you know how they calculate your position? They actually have a number of satellites surrounding the Earth that actually measure the microscopic discrepancies in time dilation between the clocks on the satellites and the clock in your phone. And they use those small discrepancies to calculate your GPS location on Earth. We use gravitational time dilation and general relativity to calculate your position so that we know where you are in Google Maps. All that craziness has a very useful application. Very cool. Okay, do they want us to say something, Stacy? I can't remember. Let's check that
Sorry,
problem.
my computer timed out. Hold on.
Professor, I got a question.
Yeah.
So the reason why the difference is not huge is because the Earth doesn't have a strong enough gravity to make a disruption.
Right, but let me also point out, Arunsak, I erased the equation now, but remember, not only the mass counts, but the radius too. Now, if you had a mass that of the sun, its radius is bigger, so the sun is also considered a relativistic weak field. But if, Arunsak, you packed the mass of the sun into the radius of the Earth, then you might start to notice, well, even then the effects would be mild. In order to get relativistic effects, you have to pack something like 3 times the mass of the sun into a volume much, much smaller than Earth. And then you really start to notice it. I think one way to measure it, Arunsak, is with the escape velocity. And I will teach you a couple of weeks from now that the escape velocity from a white dwarf is only 2% the speed of light. So that's not considered a strong gravitational field. The escape velocity from a neutron star, however, is 86% the speed of light. So you definitely notice this at neutron star level and at black hole level, but even white dwarf level is barely noticeable. Certainly not noticeable for a normal star or a normal planet. Okay, that's 59. We got one more to go. Kaitlyn, I think we're back to you if that's okay.
If you're okay with a little bit of background noise, I'm the babysitter now.
Yep, sure, we don't mind. I'll erase this, and this one doesn't need much explanation. We can just do it.
Okay, chapter, what is that? S4?
S452.
S452. Okay, yeah, hold on. I'm definitely not on the right thing. S4.
The real title
Okay.
of the problem should be gravity versus
EM force. In this, do you want me to go? Like read it?
yeah.
Okay. In this problem, we compare the strength of gravity to the strength of the electromagnetic force for two interacting electrons. Because both electrons are negatively charged, they repel each other through the electromagnetic force. Because electrons have mass, they attract each other through gravity. Let's see which effect will dominate. You will need the following information for this problem. Do you want me to read all the stuff that it has there?
Yeah, please. Sorry.
No, that's okay. So what is that? Force of gravity equals G times M1, M2 over D2. And then it has parentheses, G equals 6.67 times 10 to the negative 11.
Why don't we just 7 times 10 to the minus 11?
Yeah, that's going to be easier.
All right. And now do they give us the equation for electromagnetism?
What is it? I'm sorry.
They should also give us the equation for electromagnetism.
Yep, that is F force EM equals K Q1 Q2 over D2.
In this case, Q represents the charge of the electrons. The
Okay.
charge is
Yeah,
measured-
and then it says what K represents.
Yep, that's the electromagnetic constant. What is it?
9.0 times 10 to the 9 meters per. I don't know what. I've never seen that term before. I don't know what that is.
C stands for coulombs. That's a unit of charge.
Coulombs. We're learning about coulombs, okay?
Is it meters per coulomb or square meters?
N times meters
Oh,
squared
N is
over
Newton.
coulombs.
So
Oh,
it's
newtons, yeah.
meters squared. Newtons times meters squared. Is it over coulomb squared?
Yeah.
Okay. I should know that, but it's been a while. Okay. And what is the distance between them? They have to give us that too.
I'm sorry, what was it?
Oh, I'm sorry. I didn't realize how engaged. What's the distance between the electrons?
Let's see.
I think it's 10 to the minus 10
that?
meters.
I don't even like see where it says that. Is that mass of the electron and the charge of the electron?
Oh, we need that. What is the mass of the
Okay.
electron?
The mass is 9.10 times 10 to the negative 31 kg.
And the charge?
The charge is negative 1.6 times 10 to the negative 19 C, or coulombs.
They also should give us the distance, which I think is 10, if I remember, is 10 to the minus 10 meters.
Yeah, hold on. Yeah, distance of 10 to the negative 10 meters.
Okay. And then part A says calculate the gravity. What is part A again? Is it calculate the
Yeah,
electromagnetic?
let me read it. Sorry. Calculate the gravitational force in newtons that attract the two electrons if a distance of 10 to the negative 10 meters separates them.
Okay. So could you guys write all this intel down before we go forward? Because I'm going to have to erase it. I need more board space. Kaitlyn, since you were reading, let us know when you're done writing and then we'll proceed. You just noticed you did what? I don't understand. Oh, wow. Last week, Kaitlyn, you asked me about if they're going to shut stuff down. Jordan just sent me a text message that says, Ramundo says Rhode Island will enter a 2-week pause starting November 30th. So
That's what's up. You hear that?
No, I'm gonna fail my classes if they close this coffee shop. No cap.
that is
What she mean
scary.
pause?
Restaurants are open, she says. And retail stores. They're closing in-person colleges and universities, bar areas, recreational venues, bowling alleys. No more drinking at the bar, kids. Sad for me. Anyways, dining capacity reduced to 33% capacity. You're gonna have to wait in line and run Arunsak. So they'll be cutting the attendance at the coffee shop to 1/3 of its current value. So that could actually affect you.
Say it one more time for me. Sorry, my nephew was being sassy. I thought it was
That's
funny.
okay. You were gonna go to the Comedy Connection. Actually, they've been doing comedy over here in Kennedy Plaza on Friday nights. And I'm not much of a stand-up comedy guy, but some of those folks are really, really funny. Like I walked by one day and this guy was like heckling people making drug deals in the bushes. It was really, really funny.
I watched a guy bomb once at the Comedy Connection. He literally did like 2 jokes and he was like, never mind, I'm out. And just left the stage. It was mad funny.
You know what?
Funniest joke he made.
I feel bad because I've never been to the Comedy Connection, but I feel like the Comedy Connection is a Rhode Island rite of passage. Going and watching some towny guy bomb at comedy is like that. That's something a Rhode Islander should do. Anyways, Kaitlyn, do you have this down so I can perform the calculations and free you all?
Yeah, you're all good. Thank you.
So let me do this here. Remember all these numbers. Part A is to do the gravitational effect first, okay? Right? Part A is gravity first. Okay, the force of gravity will be big G, we're going to use 7 × 10⁻11 meters cubed per kilogram per second squared. The mass of the electron is 9.1 × 10⁻31 kilograms. Since there are 2 electrons, we have to multiply them by themselves or square it, however you like to do it. All divided by 1 × 10⁻10 meters squared. Give me your answer to 2 sig figs.
How many sig figs?
2. It's weird. We're
5
starting this
point.
pause 2 weeks from now. That doesn't make any sense. The cases, I don't know. Anyways, what?
5.8 × 10⁻61.
That doesn't sound right. It should be a small number, but not that small. I think maybe Christopher, someone else get something different.
Wait, are we supposed to use, is 9.1 × 10⁻31 supposed to be up there twice?
Yes, because it's M1 times M2, but they're
Oh,
both
okay.
they're both
right.
electrons.
Oh, I
right?
didn't square the bottom thing.
Okay.
I'm not sure if this was right, but I got 5.7 to the 11. Or no? Anybody else get that?
I
didn't
got
get 11.
5.8 times 10 to the negative 51 now.
Yeah, no, that's what I got. See, it's a.
I thought you said 11. It sounded like you said 11.
Oh, I thought you had 11 on yours.
I got that.
Why did mine say to the 11?
Here. Okay, and friends, watch. Let's just do it together, okay? 7 exp 11 negative times 9.1 exp 31 negative times 9.1 exp 31 negative divide by 1 exp 10 negative square equals. Let's just call it 6 times 10 to the negative 51. What are the units of force? Otherwise, I'm going to make you do that thing again. You guys ain't good at that. MKS units of force.
I'll be back in a second. I'm sorry.
Sure thing, bud.
Newtons.
Good. Now, part B is for us to do it for electromagnetism. So get that down, and then I have to erase. That dog is looking out the window like something's going on. All right, I'm erasing. We're so close to the end, guys. Can I erase? Stacy, you cool? All right. All right. Now we're going to do B, electromagnetism. The force of electromagnetism is 9 times 10 to the 9 Newton meters squared per Coulomb squared times the charge. What the hell was the charge again, guys? 1.6
to the negative 19.
And that's going to be coulombs twice. So we'll just square that. And that's divided by 1 times 10 to the minus 10 squared. I squared it instead of writing it out 1 times the other. That's less tedious. One sig fig will suffice.
Two times 10 to the negative 8.
Units?
What?
It's a force.
So Newton?
That's right. Coulomb squared cancel. Meters squared cancel. Newtons remain. Okay, part C, I'll read for Kaitlyn, asks us to compare the strength of gravity to electromagnetism. First of all, class, what is stronger according to our two answers? Gravity or electromagnetism?
Gravity.
Electromagnetism.
I heard two different answers. Which is it?
Well, electromagnetism is the bigger number.
Huh?
Electromagnetism is the bigger number.
Exactly. Christopher's with me. Let's compare forces. The force of electromagnetism, as Christopher points out, is much greater than the force of gravity. For electromagnetism, we got 2 times 10 to the negative 8 newtons. Gravity was 6 times 10 to the minus 51 newtons. What does that come out to be? Anyone?
3.333 whatever times 10 to the 42.
Now, electromagnetism explains why these two puppies repel each other, right? If I push these two together, there is a gravitational attraction between these two little lumps of iron, but their magnetic repulsion, I mean, 10 to the power of 42, what is that? There are names for large numbers. That is tredecillion. Tredecillion times. 3 tredecillion times greater. Tredecillion. I can say that. That's 3 tredecillion times. This is why atoms do not collapse under their own gravitational influence. And that concludes homework number 11. It took a little bit longer than I was thinking, but kind of my fault there. I was educating y'all. How dare I do that?
Are we all set, Professor?
Yep, we're all set. Please don't forget to submit those because I need to grade them this weekend.
Okay, thank you. I gotta go.
Yep, sure thing. Peace out.
Have a good one, people.
All right, everyone. Kaitlyn, do you need another minute because you were caught up for a sec, or you're good? Okay, cool. In that case, I will stop the recording and